Okay, so welcome to Math 310, Introduction to Modern Algebra. My name is Professor Miller, and what I want to do today is talk a little bit about the mechanics for the course and try to motivate why you want to take this class. What is modern algebra about? One of the nice things about teaching this class is there's many different directions you can go depending on who the teacher is. I was trained as a number theorist, so for me, I love applications to number theory. I'm going to do a lot of applications to cryptography. I do a lot of applied mathematics as well, so I will be interested in trying to see how can we use abstract algebra to solve stuff like that. So we will be moving at a somewhat fast pace. There's a lot of material to cover, and so the way I like to do my classes is 5% for class participation. If you say something in class and it's right, email me afterwards. Say what your name was, say what you said. There's a couple of reasons I do this. One, I was an introvert when I was in college. It was very hard for me to speak up, even if I thought the question was obvious and I knew the answer. I want to get you in the habit of speaking up. Even if it's an easy problem, who knows what 2 + 2 is? 4. Excellent. You could have said what base, but yeah, so 2 + 2 is 4, right? I want you to be used to speaking up. I want you to be noticed. I don't want you to be one of the people who is forgotten. So email me afterwards and say, hey, I was the one who said 2 + 2 = 4. I go, okay, great. But sometimes the questions are actually hard, and you might not realize that they're hard, and it's a really good comment. This way, when I write letters of recommendation, I can make them specific. And so the more things you say, the more likely you are to say something that's worthwhile, as well as you just get into the habit of being comfortable speaking up. It's not easy to do. It took me a long time before I became comfortable speaking up. I love the phrase first midterm, second midterm. So I normally have 2 exams, and unless you tell me otherwise, I drop whichever one is lowest. For homework, I drop whichever homework assignment helps you the most. That is not necessarily whichever homework assignment you did worse on, because every homework problem is worth 10 points. There will be ways to gain homework problem exemption. So you can put them in the bank. I trust you on the honor system that if you have a homework exemption and you want to use it for a problem, you can use it so long as you haven't handed in the homework yet. Is there anybody here who has not built a snowman? I do have the building a snowman homework exemption, but it has to be with somebody who hasn't built a snowman. So if you can find somebody on campus who has never built a snowman, do that. That is worth 10 points. Right? You should not go through college not having built a snowman. Okay? There will be more mathematical ways as well to gain homework exemptions. Final is 40%. If you want to do a project instead of having this grade scheme, happy to talk to you about things you can do. That'll count as 10%, and then I'll rescale everything accordingly. So the prereqs, we're not going to really use too much of Calc 3. We're not going to use too much of linear algebra. A lot of this is more just for mathematical maturity, so that you've seen things already. Okay, so office hours, whenever I'm around, it's office hours. If I'm not here physically, just try to find a way to. Okay, one of the things I love to do is I love to talk about providing opportunities to people. One of the reasons you go to college and don't just watch videos online is for networking, for meeting people. The more we know about you, the more likely we are to be able to help you do whatever you want to do. So I want to get to know you. I want to figure out, what do you want to do after Siena? What can we do to help you get there? A lot of life is being prepared for opportunities when they arise. So my thesis advisor is so good. I actually had 2. One of them is so good. He actually lapped the mathematics community. I was the second Steve Miller graduate student. Both of us were born same year, same city. The other one is smarter. He skipped several grades. It turns out that mathematicians and other academics, what you want as you get old is a birthday conference. And so we had a birthday conference for my advisor when he was 61. Well, there was already a Steve Miller on the advisory committee. We don't want to have 2 Steve Millers on the advisory committee. So I was just helping out a little bit. And this was a big event at the Institute for Advanced Study in Princeton. A lot of people were speaking. I was not one of the people who was asked to speak at the banquet in his honor. I was not insulted. You have a tremendous number of fields medalists, experts in the fields. Fine. I still prepared a speech just in case. And at the banquet, after the people gave their speeches, they then went out into the audience and they gave the microphone to a couple of people. And I was one of the people who was handed a microphone. And this is not a setting where you want to be unprepared. So there's a lot of times there's the known unknowns that, this is something that could arise. Be prepared, be ready to seize the opportunity. So your job is to be prepared for class. So do the reading ahead of time. This doesn't mean that if I get trapped and can't cross the Hudson that you can give the lecture. But if we're giving a talk on the Silo theorems, you should at least know what the statement of the Silo theorem is. You should know the definitions of the terms involved. You should have some idea of what we're going to talk about so the lecture can be effective. So do the reading beforehand. My job is to provide resources and to be available as needed. All right, so here's some advice from my brother. Party less than the person next to you. Take advantage of office hours and mentoring. When you're in the real world, you are frequently not going to be as fortunate as at a small college where you have people who love to teach, who love to interact. And the last is learn how to manage your time. Don't wait till the last minute. Things often take longer than expected, or something comes up that you were not planning on. If possible, try to get a strategic reserve in as many of your classes as possible. Have a terrible first week, read ahead, build up a bank so that as the semester progresses, if something happens. Are there any seniors here? Okay, how many of you are applying for jobs as seniors? Considering graduate school? For computer science, okay. So applying for jobs, applying for graduate schools, this is almost equivalent to another class in terms of the research you need to do about the various places, in terms of writing the essays. I'm happy to take a look at stuff like that. If people want to do practice interviews, I'm happy to do stuff like that. Which is more important, a introduction to algebra homework assignment or an interview that could impact the rest of your life? Well, obviously, of course, the Math 310 homework assignment is nothing more important than that right now. Unless you tell me beforehand that you have something coming up. And then, of course, prioritize that over a homework. So always happy to adjust deadlines as long as you give me at least 24 hours notice. If it's less than 24 hours, this has to be some kind of earth-shattering, the president just called me up at the last minute. I just got an opportunity to start for the Boston Red Sox in the World Series. Something of these magnitude that you could not possibly have predicted. And even then, I'm still going to be skeptical. You should not be waiting till the last minute to have things done so that if something arises, you have the ability to do it. So I almost never grant an exemption within 24 hours. More than 24 hours, I almost always grant it. So just learn to manage your time. Okay. One of the expressions you've probably heard in your life is a picture is worth 1,000 words. So whenever you are doing mathematics, and I know a lot of you are thinking about math education, you want to think about how do you present information? How do you do so efficiently? How do you so in an engaging manner? So I will admit, I grew up just outside of Boston, and if you grow up just outside of Boston, anything within 128 is your universe, and anything outside of that is the hinterland. I did not even know where Williams College was until I applied for the job there many, many years later. I knew it was somewhere in Western Mass, but what exactly is Western Mass? So North Adams is the closest major city to us, and it's not really a major city. But so I obtained, from when I was teaching in probably 2020, the plot of sunrise and sunsets. Anybody notice anything interesting about this plot? There's a lot of things you can notice. What do you notice when you look at this? So hopefully some information is being conveyed in this picture. What do you notice? Yes. Good. So there's two places where things have remarkably different behavior. So remember to email me that you made the comment. So it seems to be continuously increasing and then continuously decreasing for sunset, except at two places where there's these major changes. And what's going on at those places? Daylight savings. Daylight savings, right? And so just by looking at this, we know something interesting is happening at those 2 points, that there's some kind of change in behavior. So this is also, I believe, from 2019. The Patriots were playing the Los Angeles Rams in the Super Bowl. For this, you do need a little bit of football knowledge. When you look at this map, this is in the continental United States, who is rooting for which team or who is rooting against the other team. When you look at this, the country is pretty much uniform. Where is the country not rooting for the Rams? Yes.
Mostly in New England.
Mostly, now, does that make sense? Yes, it makes sense that in New England, they would be rooting for the New England Patriots. Where else? Yes.
Louisiana.
Louisiana. Anybody know why Louisiana? You have to know some football knowledge with this one. In the NFC Conference Championship game, the New Orleans Saints from Louisiana were playing the Los Angeles Rams. And the officials made a horrible, horrible call at the end of the game that should have allowed the Saints to run out the clock and kick a field goal to win the game. And they were so bad in the call, they actually issued an apology afterwards. Yeah, we really blew it. And so the people in Louisiana were so furious. They just despised the Rams for beating with them for this. And my friends told me they weren't showing the Super Bowl at the bars in New Orleans. They were actually repeating old Saints Super Bowls. There is one other part of the country that is not rooting for the Rams or rooting against the Rams. Can anybody tell? I'm in a little bit. Does anybody see any place which might be a little bit different? Anybody know where that is? Again, you need a little bit of football knowledge. Anybody know what city that is? What state is this next to? Yes.
Illinois.
So you have Illinois over here, and what's the other state? Yes.
Missouri.
Missouri. Anybody know what city that might be in Missouri?
Mississippi.
Not Kansas City. Anybody know any football teams from Missouri? Yes. St. Louis. Anybody know where the Rams used to play? Anybody know where the Los Angeles Rams used to play? Anybody want to guess what city the Rams used to play in? Yes. St. Louis, right? And so again, there's something going on. So when you see information like this, there should be three regions that are immediately a focus of your attention, and there's a story behind it. Most of this is just noise. Okay, everybody either hates the Pats or loves the Rams. It's more hates the Pats. So you want to think about how you're conveying information. Okay, so what I want to do now is I want to try to give a high-level overview of one of the major topics of the class and how it is useful. Is there anybody here who has not purchased something online in the past year? Okay, everybody has purchased something online. Okay, and you've all gone to the company headquarters first, met with somebody who works there, shown 3 forms of ID, done 2 forms of dual authentication, whatever, right? Blood tests to identify yourself, then had witnesses. No, right? Nobody does this. You just give them your credit card through the internet, trust that they will only charge the appropriate amount to your credit card, and they send you the product. It would be horrible if you had to physically go down and establish a working relationship with all these places. If so, then the major companies would have even bigger of a monopoly because of how much of a hassle it is. So modern commerce could not exist if we could not transmit information securely from one place to another. So when you think of cryptography, there's a couple of things you should be thinking of. One is to encrypt your data so that only the intended recipient can decode it. The next thing is efficiency. How long does it take you to encrypt it? How long does it take you to decrypt it? With modern computers, what a couple of years ago would have been a high level of security will now fall very quickly. And if quantum computers become practical, then a lot of the stuff being used right now is going to be completely open. And so new forms of encryption are being designed. World War II is a great example for a lot of encryption results. If you're planning something like D-Day, the Allied invasion of France to liberate Europe, this is something that's being planned over months. So whatever codes you have to be secure for on the order of months. During the actual battle, if you've ever seen the movie Windtalkers, this is a great example where they used Native Americans whose language was known to almost nobody outside the tribe. And so they could actually just communicate in real time just by chatting. And they would have to add some additional words. Native Americans did not have a word for tank initially. I think they used the word turtle. And so you supplement the language. And when you're using something like this, it doesn't have to be secure for months. Probably an hour or two is more than enough for an active battle scene. That as long as it would take the enemy more than, say, 1 or 2 hours to crack what you're doing, by the time they figured out, okay, you've already launched the counterattack, they already know what's coming. So depending on the application you have, it's going to take different amounts of time for you to worry about how secure something is. And so what I want to do is I want to talk a little bit about some history of cryptography and then how that's going to lead into abstract algebra. All right, so I'm going to try to switch to these slides. Let me see if this goes over. So one of the reasons you should always have at least 2 devices is this way you can see what other people are saying. If anybody, this is probably a good time to mention, is ever sick and not able to physically come to a class, I'll send you the Zoom information. You're always welcome to just Zoom in. And again, things will be recorded. All right. So how many of you have never seen anything about cryptography? Everybody has at least some basics. Okay. How many of you have heard of the Caesar cipher? Excellent. So a couple of you have heard of this. So to some extent, if you go back to Roman times, so few people could read, just writing something down is almost good enough. So the Caesar cipher, we're going to do it from an alphabet to alphabet, and we want different letters to go to different letters, and we want all letters to be hit. So it would be bad if both A and B went to the letter Q, because then if I receive a Q, I don't know what was intended. Do I need both of these conditions? These seem very reasonable conditions if I want to have some kind of alphabet code. Different letters go to different letters, and every letter is hit. So does one imply the other? Does each imply the other? What would happen if I had a letter that wasn't hit? So we have 26 letters here. Oops. Oh, I don't think I can read this. So what would happen if we can't hit every letter? If a letter Q was missed? Why wouldn't it work? Well, I'm saying, let's say that no letter is sent to Q.
You're gonna miss a letter.
I'm sorry?
You're gonna miss a letter. If different letters go to different letters and all letters are hit, if one isn't hit, then you're gonna be missing a letter.
So you're close, but you got to be a little bit more mathematical.
So if you don't hit a letter, it means 2 letters are going to the.
Good, it means 2. So if you miss a letter, 2 letters, this is the pigeonhole principle. How many of you have not heard of the pigeonhole or the box principle? So again, as a visitor, it's always a joy trying to figure out what have you done in your previous classes. And so the pigeonhole principle says, if you have a pigeon gun, don't worry, the pigeons won't be hurt, and you load in n+1 pigeons, and you shoot the pigeons into boxes, and you have n boxes. If n+1 pigeons go into n boxes, at least 1 box gets 2 pigeons. Because if each box gets at most 1 pigeon, that only accounts for n. So at least 1 box gets 2. So if we were missing a letter, then you can't have different letters going to different letters. And I'll let you do the other direction. If you had an infinite alphabet, then things would be a little bit more tricky. So one of the goals for something like this is to try to get a sense of what are the minimal conditions you need for what you're studying. A lot of times we prove things under far more restrictive conditions than we need because it makes things a little bit easier. And as you go further and further in mathematics, you ask, do I really need all this, or is it just making the argument simpler to assume that? Okay, so the typical setup is you have some input letter, let's call it x, and then f of x will be the encrypted letter. So we want to know what kind of functions can we do? Okay, we can't just say f of x equals c, the constant function. Why is that a bad choice? Yes?
Do that over multiple letters, then like, there's no like way to like prove which goes to which, like a single letter.
Yeah, so my function is f of x equals c. If I give you a 5-letter message, what do you get back? So what would you get? Tell me, what would you get for the 5-letter message? Yeah, C, 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 right? Every message would be the same. So we clearly can't use the constant function. But this is how you do things. Start off with the simplest example you can think of, and then make it hard. A lot of times, if you look at homework problems, they start you off not at the simplest case, but at an intermediate one. Try to think of an easier case first, build intuition, and then once you have that, go further. All right, so we can't do just a constant. The next simplest is the identity function would be f of x equals x. Let's do x plus c, so we shift by a constant c. And now, you have to be a little bit careful, but now different letters will go to different letters. Oops. So for instance, c equals 3 is the standard Caesar cipher. It means we shift every letter over by 3. So A goes to D, B goes to E, and so on. We have to be a little bit careful at the end of the alphabet. When we get W goes to Z, we then wrap around and X will go to A. You have seen something like this before. Okay, so right now, it seems like that clock is not even close. I was wondering how I was so far behind where we were supposed to be in such a short amount of time. Okay, I have that it's around 10 o'clock. Yes, all right. So we will use Verizon time and whatever that is on the wall. So it's 10 o'clock now. What time will it be in 5 hours? 3 p.m. Good, you said 3 p.m. So 10 plus 5 is not 3. But on a 12-hour clock, yes, 10 plus 5 is 3. We wrap around. You've used this all the time. We actually call this an abstract algebra clock arithmetic, inspired by the clock. The more fancy phrase is to use mod arithmetic or modular arithmetic. And that's what we're going to do here. So we're going to wrap around, so W will go to Z, so X will go to A. So how would we decrypt? So if you receive a message that's using this shift by 3, how would you decrypt the message? You shift back by 3. This is really not that hard to decrypt, right? How many choices are there? If you receive a message encrypted like this, how many decryption schemes could you try before you succeed?
26.
26. And then you realize I'm probably not an idiot, and you correct the 26 to
25.
25. I'm probably not going to send A to A, B to B, C to C. So there's probably, but safe. We will allow the idiot, to exist, and the idiot might have the keys and might have chosen the stupid case of C equals 0. 26 is not that many things to try. And so there's a lot of different ways to represent this. This is representing it as a nice, linear list. A goes to D, and it makes it very easy to encrypt and decrypt. If you want to encrypt, you go down. If you want to decrypt, you go up. You could also write it on a wheel. And that, I think, does a nice job of, showing the wraparound effect. And so, it's not that bad to just, write down some examples, meet at 10. Instead of, using letters, it's often better to use numbers. The reason is this is a math department. You've been spending years taking math classes. It would be nice to be able to use them. We have simple ways to add numbers. And so by converting our letters to numbers, we can then apply mathematical operations on these. And then at the end of the day, we can just convert them back to letters to read. And so encrypting, decrypting, not too bad. So there's only 25, 26 possibilities. That's not going to be that hard to crack. And you don't have to encrypt and decrypt the entire message. You only have to just start off a little bit in the beginning. And then if you notice that things are not going well, then you try the next choice, then the next choice, then the next choice. So let's make our function a little bit more complicated. So now let's look at ax plus b. So the question is, what b's are possible, what a's are possible? Rather than working with the 26-letter alphabet, let's try to get some intuition by looking at a shorter alphabet. Let's just say we have a 6-letter alphabet, A, B, C, D, E, F. And we'll let A be 1, B be 2, and so on and so forth. Just okay. Okay, so do all B work? Do all A work? Can you think of any A's and B's that might work? We can really break this up as two operations. We can first multiply X by A, and then we can shift by B. Is there going to be any issues with shifting by B? Is there any danger that two letters could be mapped to the same letter when we shift every letter by the same amount? No, the shifting by B is going to be very easy. All shifts by B will be fine. And we already know how to do a shift by B, so we really want to just focus on which A's are possible. That's going to be the interesting part. All right, so it's enough to study A. We can take B equals 0 for simplicity, and then we can put in that shift by B later without any trouble. So we're looking at f of x equals ax, and we want different letters to go to different letters. What's the easiest value of A to check? Easiest value of A. 1. So every letter goes to itself. Is that going to work? Yeah, right? No letter is going to be mapped to the same thing as anything. So A equals 1 will work. Okay. So if we take A equals 1, we get 1, 2, 3, 4, 5, 6. If A equals 2, we have trouble. So we're multiplying by 2. So 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. But what is 8 when we have a 6-letter alphabet? 8 is the same as 2. It's like a clock with 6 hours. So we'd get 2, 4, 6, 2, 4, 6. And now I say because 2 fails, 4 and 6 will also fail. Because you can view 4 as multiply by 2 and then multiply by 2. So if you multiply by 2 and 2 letters collide, then if you multiply by 2 again, you're still going to have the collision. If you multiply by 3, you're still going to have the collision. So this is not necessary. I could have checked 4 and 6 separately, but this is just being intelligent. Once I notice 2 failed, I get for free that 4 and 6 fail as well. Okay, similarly, if we try 3, we're going to have issues. 1 goes to 3, 2 goes to 6, 2 times 3 is 6, but then 3 times 3 is 9, which is the same as 3. It's going to repeat. So 3 fails. 5 turns out to work. With 5, we get 5, 4, 3, 2, 1, 6. So the numbers that work are 1 and 5, and 2, 3, and 6 fail. So does anybody know what the numbers 1 and 5 have in common? What do 2, 3, 4, and 6 have in common? I see all of the markers have been collected on this side of the button. So we're looking at a 6-letter alphabet, and we have 1 and 5 work, and we have 2, 3, 4, and 6 fail. Yes.
1, 5, sure, GCD is 6.
Good. So these are relatively prime to 6. How confident are you that you've discovered what goes on with one data point?
Not that confident. Maybe.
You want to bet your semester grade on it right now?
No.
Anybody ever see Legally Blonde? The scene with would you bet your, well, that's what you're doing when you go to court. what could you do to gain confidence?
Add more data.
Add more data points. Give me some other some other numbers for the size of the alphabet. Give me 3 other choices.
Like, what A could equal?
Yeah.
10.
10,
11.
11.
15.
And for those 3, doing calculations, the only ones that work are the numbers that are relatively prime. Are you more confident now?
Yeah.
Now, but maybe you chose numbers that have special properties. So you want to try to choose what's the, if you only have so much time to test, maybe I want to test a prime, maybe I want to test the product of 2 primes, a prime squared. 6 is a composite number. Maybe there's some issue going on because it's composite. And so I will tell you that everything up to 1.35 billion, only the relatively prime ones work. Now you should be very confident, but it's possible that there could be an exception later. If you can, I strongly urge all of my students to learn how to program or learn how to ask AI to program for them and understand the code that's being generated so that you can gather data. It is the 21st century. You need to be able to gather and analyze data. And so at this point, we're beginning to make a conjecture that the numbers that work are going to be the numbers that are relatively prime to the size of the alphabet. Okay, so you got the pattern. So what do you think would work for the 26-letter alphabet? So if your conjecture is correct, which numbers would work or which numbers would fail? Yes.
Numbers that are relatively prime.
Okay, which ones will be relatively prime to 26? What can you immediately throw away?
1.
One will work. Are there any numbers that you immediately know are going to be that are going to share a factor with 26? I'm sorry, 26. There's a large class of numbers that you can immediately get will share a factor with 26. 13. There's a more basic set of numbers. The evens, right? You throw away all the evens and you throw away 13. So it's going to be an odd number. And as long as it's not a multiple of 13, so we're using a deep fact here that numbers have unique decompositions as products of primes. So what's going to work is 1, 3, 5, 7, 9, 11, miss 13, 15, 17, 19, 21, 23, 25. And there's 12 such numbers. So in a question like this, what's important is not necessarily just which ones work, but how many are there that work. So if you think about it, we're looking at functions of the form ax plus b. We have 26 choices for b. Initially, we could have had 26 choices for a. We don't. We only have 12. But 12 times 26 is still a lot more than 26. It's more than 10 times as much. Is this going to be a hard code for a computer to break? No, we're talking about, on the order of, less than 500 things to try. The computer is going to blow through this in no time at all. But, it's still a little bit better. And, we keep trying to make things harder and harder and harder. And hopefully you can begin to see some of the number theory and what we'll later reimage as algebra coming into play. Okay. So I'll just leave for you to think about how else could we try to generalize this? Could we look at functions of a higher degree? Could I have a quadratic? Because if I had a quadratic, I would now have 3 coefficients. But if I had a quadratic, would I have trouble with 2 letters being mapped to the same letter? So I'll leave that as something for you to think about. We are going to see the Euler-Toscan function many, many times in this semester. So phi of n is the number of numbers from 1 to n that are relatively prime to n. So it counts how many numbers from 1 to n share no factor with n other than 1. So in mathematics, you have to always be careful about how do you define things. Can somebody define the factorial function for me? Like, what's 3 factorial? Yes,
3 times 2 times 1.
3 times 2 times 1. Do you know what the factorial function represents?
I guess multiplication of all values from n to 1.
Good, but can you give me a combinatorial story? If I have 3 people, what does 3 factorial represent?
All the different combinations or permutations.
You gotta be specific. What kind of permutations, what kind of? Yes,
3 choose 1.
it's not 3 choose 1, that's something different. 3 choose 1 is choosing 1 person from 3. What is 3 times 2 times 1? If I have 3 people, yes.
I feel like the amount of ways that you can like reorder the people without making the same.
It's close. It's the number of ways to order people where order matters. So president, vice president, secretary. The president is not the same as the secretary. So if I have 3 people, there are 3 factorial or 6 ways to assign the 3 positions to them. If I have 8 people and I want to choose 3 people from 8 to hold these offices, and it matters who gets which office, it'd be 8 times 7 times 6. If I don't care, if I'm doing, say, representatives and student council, and all representatives are the same, then it would be, how many ways can I choose 3 people from 8? And then that would be the 8 choose 3. What's 0 factorial? 1. We decided as a community that 0 factorial should be 1. 0 factorial does not mean 0 times something. 0 factorial is how many ways are there to order no people, where order matters. This is the Seinfeld, there's 1 way to do nothing. Okay, that's what we've decided 0 factorial should be. It's a convenient definition. It makes a lot of formulas work nicely. If I give you any 2 integers, is there a number that divides both integers? One. So if I want to talk about do numbers have a common factor, well, 1 divides everything. So if I don't take into account the fact that 1 has some special properties, this is going to be a stupid definition because any 2 numbers are divisible by 1. So we count how many numbers are there from 1 to n that are relatively prime to n. So if you share 1 as a factor and that's the only factor you share, we will call you relatively prime. So if p is a prime number, so let's say p equals 7, how many numbers from 1 to 7 share no factors with 7? So if the numbers 1, 2, 3, 4, 5, 6, and 7, which of these share a factor with 7? One is it, but we don't care about 1 because the only factor it shares with 7 is 1. So just 7. Because otherwise, by your argument, I could say, well, 3 and 7 share a factor of 1. So we want them to share a factor greater than 1. So the only number that shares a factor greater than 1 with 7 is 7. So what would phi of 7 be? How many numbers from 1 to 7 are relatively prime to 7? Not 5, 6. What if I gave you 11? How many numbers from 1 to 11 share a factor greater than 1 with 11? What's that?
This one.
Just 1. Which one is that? 11. And so what would phi of 11 be? 10. So in general, if I gave you some prime p, how many numbers from 1 to p are relatively prime to p if p is a prime? It would just be p minus 1. So try to write that up rigorously. Try to write this up carefully, that the number of numbers relatively prime to p is p minus 1. Okay, so now let's start building on that knowledge. I just realized, okay, so not only is the clock wrong, but the clock is not moving. Okay. So the next simplest thing we could think of is one of two possibilities. Building on my success at understanding phi of p, I could look at phi of p squared, or I could look at phi of pq, where p and q are two distinct primes. So I could try to build things up for lots of different choices of p. I could do phi of 2 squared, phi of 3 squared, phi of 5 squared, 3 of 7 squared. I can collect data. And so, I urge you to go home and do some of these calculations and try to notice a pattern. In the interest of time, I'm not going to go through and collect all that data. Let's just see if we can think about things. So let's take an arbitrary prime, let's do 7, and let's look at p equals 7. So we have 1, 2, 3, 7. What's the next row going to be? I'm running all my numbers from 1 to p squared. P squared is 49. What would start the next row? So what would start the next row?
1, 4,
Nope. I'm going with numbers from 1 to 49. I have 1, 2, 3, 4, 5, 6, 7. What comes next? Basic counting. 8, right? 9, 10, all the way up to 14. Next row. 15, all the way up to, and we keep going all the way up to 49. If I write my grid like this, can you show me which numbers are multiples of 7? Which ones are they? Yeah, this is why I wrote it like this. It's really easy to see which are the multiples of 7. Are there any multiples of 49? Anything in this list is a multiple of 49. 49. Well, I've already crossed 49 off. I can cross it off again, doesn't matter. So if I look at this, the only numbers that can share a factor with 49, you have to either be a multiple of 7 or a multiple of 49. Well, if you're divisible by 7, so if you're divisible by 49, you're going to be divisible by 7. I just have to look at multiples of 7. So what's the answer? How many numbers from 1 to 49 are relatively prime to 49? Phi of 49 is what? I'm sorry? Why 48? That's only if it's a prime. Phi of a prime is p minus 1. So we have the table here. How many numbers did we lose? 7. How many did we start with? 49. So it's 49 minus 7. How might you write 49 minus 7? You could write as 42, which is the meaning of life. But how else could you write it in terms of stuff in this problem? Yes. You could do it as p times p minus 1. How else could you do it? There's another way you could write it. It's very similar to p times p minus 1.
P squared minus p.
Yeah. I mean, this is highly suggestive looking at the table that it should be p squared minus p. We have a table that's p by p. We have p squared elements, and we only lose the p at the far right. So it looks like it should be p squared minus p, and then that simplifies to p times p minus p. So that turns out to be correct. So we lose 2p, 3p, all the way up to p squared. Okay? And then you could try to figure out what would p cubed be. Which multiples of p do you lose when you have p cubed? And I'll leave that as an exercise that it's p cubed minus p squared. And now if you look at it, it looks like a pattern is emerging. Phi of p is p minus 1. Phi of p squared is p squared minus p. Phi of p cubed is p cubed minus p squared. How could I write that 1 in a more illuminating manner?
p to the power of 0.
Yeah, p to the power of 0. What would you guess phi of p to the 4th is?
P to the 4th minus p to the 3rd.
Yeah, p to the 4th minus. So there's a pattern that's emerging. And if you have an idea of what you're trying to prove, it makes it a lot easier to prove it. The next thing is to look at, what if I give you two distinct primes what is phi of their product? It turns out for a lot of encryption, this is all we need to know. When we start studying groups, we will actually care about phi of any integer n. But it turns out for cryptography, for the most part, we really just need to know what phi of pq is. So if I give you two distinct primes, I need to figure out how many numbers from 1 to pq are relatively prime to p and q. So how many numbers are there from 1 to pq? How many numbers do we have in total? We have pq numbers. So what we're going to do is something that's a really simple inclusion exclusion. So we start off, we have pq numbers. How many multiples of p are there less than or equal to pq? Nope. Q. I have p, 2p, 3p, all the way up to qp. So I have to subtract off q multiples of p. How many multiples of q do I have? I have q, 2q, 3q. I won't say the next one. I have p. And so I've thrown away all the multiples of p. I've thrown away all the multiples of q. But if something is a multiple of both p and q, I threw it away twice. I should have only thrown it away once, so I have to add it back. How many numbers from 1 to pq are multiples of p and q? Only pq, so I have to add one back. And now what's interesting is you can write this as p minus 1 times q minus 1. Let me try to find a better marker. And what do you recognize p minus 1 as? So this is phi of p times phi of q. This is really nice. Phi of a product is the product of the phis, at least if the inputs are relatively prime primes. It's not the case in general. Phi of p squared, that's phi of p times p. That's not phi of p times phi of p. So the function is not always going to be multiplicative like this. But again, what you want to be able to do is you want to look at simple cases, build up some intuition. And so what we're seeing here is, and this is just writing it down explicitly, we lose q multiples of p, we lose p multiples of q, we double counted pq, so we add it back, and that's why we get p minus 1 times q minus 1 after we just do some algebra and simplify things. So we can now calculate how many numbers are relatively prime. We've seen a little bit of an application of this in terms of trying to look at improving the Caesar cipher by going to ax plus b rather than just a shift. It turns out this is going to have a lot more powerful applications than just that. So what I want to talk about now briefly is the binary and permutation ciphers. So if you see a long string of text and somebody is using a simple cipher where a given letter always goes to the same letter, what do you think the most common letter decodes to in English?
Okay.
Any other choices? I would do E over A. How do we determine who's right? Gather data, right? Look at data. If you see the same 3 letters again and again and again, what do you think a really common 3-letter occurrence might be in English? The. And so nothing against your parents, but a lot of people who are not professional mathematicians are able to solve the encryptions that are in a lot of newspapers, where they're permutation ciphers. So for permutation cipher, each letter goes to a different letter. And I'll probably explicitly write this down a little bit later, but you have 26 letters. How many permutation ciphers could you do? So you have to choose which What does A go to? What does B go to? What does C go to? How many choices do we have? 26 factorial, and we'll see later, 26 factorial is a decent number. It's enough so that your mom and dad at home are not going to be able to go through all 26 factorial possibilities, and their computer can't do that as well. But if you have English text spelled correctly, and you have a one-letter word, what is that word almost surely? What are the possibilities? A or I, right? And so you can start doing things like this. If it ends with an NG, maybe it's an ING before that. If you see it HE and there's a one letter before, maybe it's a, so there's a lot of things you can do. You could deliberately try to misspell things. You could put in extra letters to try to make it harder for people. But if you have a standard normal text, it's not a problem. The Vigneri cipher was a brilliant idea. What you do is you take a keyword or a phrase and you just write it under your message. And then what you do is you do a Caesar cipher based on the letter. And so if I do ABC, 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 I'm going to shift the first D by 1. I'm going to shift the A by 2. I'm going to shift the second D by 3. And so now using the Vigneri cipher, the same letter is not always encrypted the same way. This makes it more challenging to decrypt. If, however, you know the length of the key phrase, what you can do is you just break the message up into thirds. Look at the first third, look at the second third, look at the third third. If your message is very long, what should the most common letter be in the first third of the message? What would you guess? Most common letter in the first third of your message. E. What would you guess is the most common letter? Oh, sorry, I was saying word. What's the most common letter in the first third of the message? E. What's the most common letter in the second third of the message? E. And what is the most common letter in the last third of the message? E, right? Now, there is a novel that was written without the letter E in English. If somebody gives you that, good luck. But good initial guess, see whatever letter is the most common, make that the E. The hard part is figuring out what is the length of the phrase. It turns out that there are ways to sniff out what the length of the phrase is. This is always one of the dangers, that you have a lot of these elementary methods that seem hard, but somebody might find a nice high-powered way around it. And so you do have to be a little bit careful. And the question is, how secure is this? So if you're interested, there's a bunch of links you can look at. One of my favorites, who knows about the siege of Vicksburg in the Civil War? It fell to Grant on July 4th. A little bit before it was taken back by the Union, the South sent a messenger. And when the messenger arrived and saw the Union flag flying, he threw the message into the river and departed. Over 100 years later, somebody actually found the message in the river. And it would have been trivial to crack this with modern computers, but people said, well, let's see if we could crack it using 1860s technology. And they knew who again, I might get some of the details slightly off, I apologize. They knew who the general commanding was of Vicksburg. So they guessed, maybe the message begins, "Dear General." And by doing something like that, they were able to decrypt the message. The message basically said, we have no forces to share, you're on your own, good luck. And so, but again, these small little dangers you can do that people can exploit. They did this in World War II for the German Enigma. There was a German station that began the day by broadcasting twice the weather report. Really nice to know, because if you know what the weather is, you can then use this and have a clue in terms of how to decrypt things. So you can have a very secure method, but if you make one or two small mistakes, it can be exploited. Okay, so we mentioned that there's 26 factorial permutation ciphers. I don't expect anybody to have memorized what 26 factorial is. I did the calculation beforehand. It's about 4 times 10 to the 26. So if you want to think about how powerful your computer is, you can do some quick calculations and see just if your computer could try 10 to the 14 possibilities a second, how long would it take to try all 10 to the 26? And it's going to be a decent amount of time. So the permutation ciphers are somewhat secure, but they are amenable to various types of attacks. So one of them is the frequency analysis. So I was actually good. I actually gave a web link to where I got the data from. I sadly do not always remember to do that. And so according to frequency analysis of almost 10,000 English works from Project Gutenberg, E is occurring about 12.58% of the time, leading Z only about 0.08% of the time. And so you can try to use this to gain, a couple of letters. And again, if you have spaces, it makes it a lot easier. You can also look at bigrams and trigrams, the most common 2- and 3-letter phrases. And again, stuff like this can really help you in terms of cracking a permutation cipher. Permutation ciphers are not that hard, even with the spaces removed. Okay, so what I want to talk a little bit now is Y primes. So, right now we're doing, some standard stuff and just looking at all permutations. I want to try to explain to you why prime numbers enter the realm of cryptography, which is going to then enter us in our introduction to modern algebra. So imagine P and Q are 200-digit primes. Those are big numbers, okay? And what I want to do is I want to give you a sense of how one of the most famous encryption standards for years, the RSA algorithm, works. And to describe that is going to get us to a lot of the key ideas of abstract algebra. So there are two systems, and you have to tell me which system do you think is more secure. In system one, I choose two primes, P and Q. They are 200-digit numbers. How many 200-digit numbers are there, approximately? Approximately how many numbers have 200 digits? Nope, not 200 factorial. Nope. Nope, I want a 200-digit number. How many choices do I have for the first digit? 9. How many choices do I have for the second digit? Nope. How many choices do I have for the second digit of my number? 10. How many choices do I have for my third digit? How many for my fourth digit? How many for my fifth digit? Every digit I have 10 choices but the first. I'll just call the first we have 10 choices. So how many 200-digit numbers are there, roughly? 10 to the 200. Right. Does anybody have a sense of how big 10 to the 200 is? Right.
It's bigger than all the particles.
So anybody know roughly how many particles do these thingamabob-jigs there are in the universe? 10 to the, we'll use 10 to the 80. I'll round up to 10 to the 90 to be safe. Well, we'll use your 10 to the 80. So we have 10 to the 80 objects in the universe. Let's imagine every object in the universe is a universe. How many particles would you have if every object in the universe is a universe? Not to the 10 to the 80. It would be times
10 to the 80.
times 10 to the 80, because every object is another universe. That's 10 to the 160. Okay. Let's assume your computer can do 10 to the 14 calculations per second. And let's assume every particle in this universe of universes is a supercomputer devoted exclusively to you. Okay. Then you could check 10 to the 160 times 10 to the 14 equals 10 to the 174 items in 1 second. If you had a universe of universes of supercomputers devoted to you. I just met somebody today who said IT at Siena is very good. We will push them. Okay. Anybody know how many seconds there are in a minute? 60. I don't want to do 60. I'm going to do 100. I'm going to round up. How many minutes are there in an hour?
60.
Let's round up 100, right? Do you really want to be multiple? How many hours are there in a day?
24.
And let's round up to 100. How many days in a year?
5.
And let's round up to? No, 1,000. So 3, 4, 5, 6, 7, 8, 9. That's 10 to the 9. 10 to the 9 seconds per year. Anybody know roughly how old we say the universe is? 13 billion years. Let's round up to 100 billion. Do I need more zeros than that? See, that would be a million. That should be right, correct? And how many is that? That's 10 to the 11. So we put all this together, that's going to be 10 to the 20 seconds since the universe was created. We have the 10 to the 174. That's 10 to the 194. So rounding up to just give you a sense of how difficult the problem is. If I want to just list all the 200-digit numbers with a universe of universes of supercomputers devoted exclusively to my use, running since the dawn of time, with a lot of overestimation, I'm 6 orders of magnitude too small. Okay? This should hopefully show you that brute force is not going to be enough. There's an old joke that Carl Sagan was giving a lecture, and somebody in the audience wasn't really paying too much attention. They were kind of tired, and then they joked up when Sagan said something about the sun exploding. Wait, could you say that again? Do you know the joke?
What?
Do you know the joke? Or you?
No.
Okay. So the person, what did you say? What did you say? I said the sun is going to go nova and explode in about 5 billion years. Oh, thank God. I thought you said 5 million. Does it really matter for most of us if it explodes in 5 million or 5 billion? No. There are so many 200-digit numbers. Even though in the limit almost no numbers are prime, the number of primes up to x is about x over log of x. So the number of primes up to 10 to the 200 is about 10 to the 200 over the log. It's about 200 times the log of 10 base e. This is less than 1,000. This is like 10 to the 198. Or 97. There's so many primes with 200 digits that if I want to just try all the primes, a universe of universes of supercomputers running since the dawn of time is still going to be 1,000 orders of magnitude too small to check them all. So system 1 is choose two 200-digit primes, multiply them, and your password is either P or Q. So there's 2 passwords that work. Okay. The other method is to choose a 5,000 random digit number. How many 5,000 digit numbers are there? Approximately 10 to the 5,000. So which do you think is more secure? You have to guess a 5,000 digit number and get all the digits right, or you have to guess one of the 200 digit primes that I've chosen, and I even tell you what the product is, so if you can factor n, you can get the password. Which do you think is going to be more secure? I tell you what n is, and you just have to give me either P or Q, and they have 200 digits. So there's on the order of 10 to the 200 things to try, or you have to give me a 5,000 random digit string. Which do you think seems more secure? It's okay if you're wrong, but which seems harder to get? The 5,000 seems harder. You've got to get 5,000 things right versus 200. And there's even 2 different 200-digit things that work. It turns out the 5,000 digit is not as secure. How does the computer tell if you have the correct 5,000 digit number? Yes.
I thought you were first.
Okay. Okay, so I'll ask the first question. How does the computer tell if you are correct?
The number n is divisible by the number.
Does the computer need to know the password? No, I will know it when I hear it. You have this stupid gatekeeper. I don't know the password, but I'll know it when I hear it. For the second one, does the computer need to know the password? Yes, you actually have the ability to torture the computer. It has to be written down somewhere for the computer so you could actually try to look at the innards. A lot of times when primes are created for certain security purposes, they destroy the computer that was used to create the prime. Because once you have this, the computer does not need to know. So yes, it's harder to get 5,000 digits right than 200 digits right, but I hope this exercise shows you that there is so much security right now, we believe, with a 200-digit prime, that we're really not that worried about somebody just guessing a 200-digit prime. What we're worried about is there might be a fast, easy way to factor a number that we don't know about. If somebody can quickly factor numbers, then I can easily get P and Q. No one has publicly announced that they know how to factor quickly. We will later see a very fast way to tell if certain numbers are prime or composite. And we can tell certain numbers are composite without telling you any of their factors, which seems strange. What does it mean for a number to be composite? It's divisible by at least 2 primes. It can be written as x times y, where x and y are both greater than 1. And so we can tell certain numbers are composite without being able to tell how they factor. So this is a existence proof that's non-constructive. You have seen this before. Do you remember any results from calculus where you know something exists without necessarily being able to find it?
Inverse of projection.
What do you mean by the inverse of a projection?
A shadow.
Right.
You can tell that there's something there, but not necessarily what shape exactly made that shadow.
Okay, okay, so you've lost some information. Okay, yes. That'd be more linear. I'm trying to think of a calculus example. So there's 2 theorems from calculus where things are known to exist, but you don't know how to, you don't explicitly given.
Plus C on the end of the. Yeah.
Nope. So that's just finding all the antiderivatives. So it's usually it's done in Calc 1. 3-letter theorems. The intermediate value theorem. If you are 20 miles from home and you end 50 miles from home, at some point you are 30 miles from home. You hit all intermediate values if you walk continuously. There's no transporter from Star Trek where you just jump instantaneously from one spot to another. If I go from 20 miles to 50 miles, I must have passed through 30, I must have passed through 35. The other one is the mean value theorem. At some point in time, if my function is differentiable, my instantaneous speed is my average speed. If my average speed is 50 miles per hour, and I'm always traveling below 50 miles per hour, that's impossible. If my average speed is 50 miles per hour and I'm always traveling above 50 miles per hour, that's impossible. So at some point in time, I must be traveling my average speed. And so there are a lot of examples of things in mathematics where we can prove something happens without being able to construct it. We can't give you the specific example, but we know that some example exists. We know some point exists. We know something has one of these properties. So it turns out that the first system is the more secure one. And then over here, oops, I was just writing down the calculation we were doing on the board. I was doing 10 to the 80 such objects in the universe, so I'm glad that we were on the same page. I guess I was a little bit more generous. I said the computer could do 10 to the 15 rather than 10 to the 14. And we just see that a universe of universes of supercomputers running since the dawn of time is not enough to brute force this problem. So unless there's a backdoor, unless there's an easier way to get to it, this should be a good level of security. Right. What I want to do for the last few minutes is give you a sense of some of the more advanced concepts that we're going to get to later in the semester, and just show you where things are going. So this is the RSA algorithm named for the 3 people who popularized it. And then, there's always interesting history as how much was known before they popularized it and was just kept classified. So the British actually knew a lot of this as well. It's one of the difficulties in writing the history of the subject in that a lot of things have to be kept secret. So it's not enough to keep something secret until somebody else discovers it. You don't want people to know that for the last, say, 10 years, you've been able to crack their codes. Because then that impacts people because they can say, you're doing behavior now and recently based on having cracked our codes and knowing what we're doing. So you have to keep information secret for long periods of time. So there are a couple of rules in mathematics in terms of naming. You have to use Alice and Bob. You do have a little bit of freedom. The evil person can either be Charlie or Eve for eavesdropping. You have that level of freedom, but it's always Alice and Bob, and Alice is always sending a message to Bob. And we're going to send messages by sending numbers. And I could put more subscripts on the letters so that when you glance down, it's a little bit easier. Bob is going to choose 2 primes. They're going to be large primes, but just so it fits on the page, I'm going to do 5-digit primes. 15217 and 17569. I could put P sub B and Q sub B so that I know that these are Bob's primes. And Bob is going to choose some number D, and he's going to keep these 3 numbers secret. So only Bob knows these numbers. Bob is going to make public the product PQ and a special number E. Anybody know why I chose this E? Yeah, it ends 2, 6, and I round up to 3. So I deliberately chose this E and then went backwards to get what D would go with that. So Bob makes the stuff in blue public. He keeps the stuff in red secret. And it turns out E times D has a really interesting property. If you multiply E and D, you get 1 on a clock with P minus 1, Q minus 1 hours. Does anybody recognize P minus 1, Q minus 1? Where have we seen that before? 5P times 5Q. What's nice in the first day of class is, where have we seen this before? It's got to be earlier today, right? There's no other choice on the first day of class. So the Euler-Toshin function is playing a role here. So E was chosen very carefully with respect to D. Now, it's not clear that you'll always be able to find a number E that has this property. We'll have to show that there will always be such an E. The hope is that just by making N and E public, there's no easy way for Eve or Charlie to figure out what P and Q are. Nobody has publicly stated a way to do that. There may be a way, but if so, nobody knows how to do that. And now what we're going to do is we're going to send a message. And N is going to be P times Q. We're going to send a message that's any number less than N. And if your message, is longer, then you just break it up into smaller messages. So maybe 00 is A, 01 is B, 02 is C. We can go all the way up to 99. We can have some special symbols. We can have Greek letters. We can have math functions, parentheses, grammatical symbols. So we just break the message up into blocks of size N. And we take the message M that we want to send. It's going to be some number. And what Alice does is she takes the message and she raises it to the eth power and takes the remainder when we divide by N. So imagine we have a clock with N hours and we just reduce it mod N. So if N was 12 and we got the message 35, we subtract off 12 from 35 and we get 35 minus 12 is 23. We subtract off 12, we get 11. So then the message would be 11. It's just a little bit harder now because N is 267347473. It's a little bit bigger. And now the other thing is we're raising our message to a huge number, 3141,593. That's a lot of multiplications. That's over 3 million multiplications if we just do it the naive way. And we need to really think about P and Q being 200-digit primes So how big would n be if P and Q are 200 digits? So if P and Q are 200 digits, how big would n be? If you have the product of two 200-digit numbers, how many digits would the product have? 400. So we would be raising a message to 10 to the 400. 10 to the 400 multiplications. We can't do 10 to the 400 multiplications. We can't even do 10 to the 20 multiplications. So this is pure mathematics at its greatest. Oh, yeah, I just raise it to that number. Okay, and how do we do this before the universe dies a heat death? So we need to find an efficient way to do that. It turns out that there is an efficient way to do this, and we will see how to do that efficiently. But right now, I'm just saying, just do this. And then the way you decrypt is you take X and you raise it to the dth power. So X is the message that Bob receives. And all these are in the notes. You can go through, you can try to do this at home. And you can see that you will actually get back the original message when you do this, that somehow it undoes things. So this is absolutely wonderful. Now, what's nice is if you take the Caesar cipher, you shift every letter by 3. Imagine there was some static and you received one letter incorrectly, but every other letter is correct. Do you think you can still figure out what the message is if one letter is off? Yes. Imagine there was some static and we got one digit wrong. We were supposed to get 7-3, we got 8-3. If we now apply this, it's unfortunately cut off, we get 121141028. Only 2 digits of the final decrypted message match the correct message. If you think about it, if I were to just randomly write down a number, what percent of the time do you think my digits would match the actual digits? So if you have a message and I just randomly write down strings of numbers, what fraction of the time do you think my digit matches your digit? What would you guess? Yeah.
Like 10 to the negative amount of digits that you have. So like, because you multiply, each digit has like 1 in 10 chance.
Good. So each digit has 1 in 10 chance. And so if I have D digits, I would expect D over 10 to be correct. So I expect about 1 in 10 digits to be right. Well, my message has 2, 4, 6, it has 9 digits. So I would expect 1 digit to be right. Am I surprised that I got 2 out of 9 right? No, that's pretty close to just 1, small fluctuations. That's not unreasonable. So if you have just one small error, you get complete gobbledygook afterwards. So this means we have to be very careful when we transmit information. How do we transmit information so that if there is an issue, we can correct it? And this leads to error detecting, error correcting codes, where the computer can realize the mistake was made and fix it in real time. So there's going to be a lot of implementation issues. How do we find large primes? How large is large enough for us to be secure? Is it possible to find E and D so that E times D equals 1 mod P minus 1, Q minus 1? How can we compute M to the E mod N efficiently? We can't do 10 to the 400 multiplications. And then the really dangerous one is, can Eve somehow determine the D for decrypt? There's a lot of other problems that we can talk about once we have this. Let's imagine you are Bob and Alice is a really good friend of yours. You've known Alice for a long time. You trust Alice completely. And you get a message that says, Bob, I'm in trouble. I need $5,000 fast. Please wire it to this account or it's going to be lights out for me. Love you, Alice. What do you do if you're Bob? What do you do? It's a, why do you think it's a scam? I mean, because it was signed Eve, I'm sorry, signed Alice, right? With love. All right, so you get a new message from Alice. Bob, it's Alice. I need $5,000 really fast. This is not a scam. Love, Alice. P.S. Go Nairobi. What would you want to do if you were Bob? I'm sorry? I'm sorry? What is that? Oh, you would want to contact Alice, right? But you can't. Alice can only send one message. What does Alice need to do in her message? What's Alice's objective if this is really coming from Alice? So Alice needs the $5,000, but how is Alice going to convince Bob to send the $5,000? Because Bob is going to consider this a scam. What does Alice need to be able to do in the message? Encrypted in what way?
Encrypted and send the information decrypted in that message, so.
But how is that going to help Bob? What does Alice need to do? What's Alice's objective right now?
Confirm that it's her sending.
She needs Bob to know it's her. So how could you confirm to one of your friends that you are you? What could you do? How would you convince somebody that you are you and not an AI chatbot or a spammer? Yes.
Tell them something only you know.
But it would be tell them something that only the two of you know, that only the two of you share. So if the two of you have a relationship, you might be able to do something like that. You might not be able to do that with an arbitrary person, but hopefully you would have enough of a relationship with Bob that you could send something that would clearly determine that you are you. So it turns out that using the techniques we have here, there's a way for Alice to choose some primes and make them public. And Alice can have something encrypted in her message that can verify that she really is who she says she is. And so there's a lot of really good math lurking in all of this. So, again, we did a lot today. I want to try to give you a sense of where are we going in this course. And so, part of this was I want to get a sense of, what math have you seen? The first chapter of the book is a review of some mathematics. It has the binomial theorem, it has Pascal's triangle. We'll talk about some of that stuff on Thursday's lecture. So you should read all of chapter 1 and you should start reading chapter 2. I don't think we're going to get into too much of chapter 2, but we might start, some of the beginning. I will have, throughout the semester, some, fun games involving abstract algebra that if you are going to be eventually going into classrooms, you can use those for things there. But, right now, just, look at chapter 1. If anything is truly, truly new to you, send me an email so I have an idea of what to spend more time on in the next lecture. And then hopefully you have a sense of what you're doing is at least useful. There's a lot of classes where at the end of the year, if you can't answer the who gives a damn question, we have failed you. Sometimes it's, well, I need this to get my license. I need this to get the degree. My brother, we're about to have a technical malfunction.